Okay, hello, welcome back. So in the previous video, we introduced the general concept of moment of inertia. But now let's look at a few practical aspects of this moment of inertia. First thing I want to say is that moment of inertia is, well, it is a very complex concept. And in 3D rotations, it becomes not a scalar, not a vector, but a tensor or a 3x3 matrix. So it is a quite complex property, mathematically speaking, when you go to 3D rotations. But in 2D, we can stay happy and work with a scalar value. But noting that moment of inertia is calculated about an axis for the entire body. So you don't really calculate moment of inertia about a point, but an axis that passes through a point, for instance. So you calculate moment of inertia about this axis A. And you calculate all the distances from that axis of all particles, you take the integral. So first thing is, note that it is an axis dependent property. Another thing I want to say here is that how do you take this integral over the entire mass? Often maybe complicated. What you can do to practically calculate, you can use, well, you have to convert this integral to something with definite bounds that you can actually calculate with numbers. What you can do is to transform this to a triple integral if you are dealing with 3D bodies. And instead of dm, you can write rho, the density times the volume of that dx, dy, dz. So you can convert that to an integration over physical spatial dimensions, x, y, z, and that's how you can calculate it. If everything is kind of symmetric in one dimension, like about z, that's what we usually do. So we have a particle looking from above. This is my axis A now. The entire body essentially flattens out. You can get away with, this is dy, dx, this is x, this is y, and you can calculate I about this point or axis A that passes through the point as a double integral of r squared, which is x squared plus y squared, dx, dy, and the rho comes out. And from the bounds of the edges of the body. So you can calculate these bounds of integral. That's how you can calculate it. Another thing to think about is moments of inertia, just the same way inertia would add up. So you have 1 kilo of one particle plus another kilo of another particle. The total mass would be 2 kilos. You can also add the moments of inertia of particles or bodies about the same axis. So there are many tables. There are in the textbook and Wikipedia or Google, anywhere. Moment of inertia for many of simple geometries are available. For instance, moment of inertia for a box or for a circle about its center, and so on. They are all available. And what you can do if you have a complex system, for instance, like this, like that, you can add the moments of inertia. Well, let me change this a little. so it looks nicer. This is a rectangle attached to a circle, for instance. You can add up the moments of inertia to calculate the compound moment of inertia of your entire body. So this moment of inertia equals this plus that. And you know this. But a very important but here is that all these moments of inertia must be calculated about the same point. For instance, if it is a hammer or whatever, you want to calculate moment of inertia about its endpoint. You have to calculate moment of inertia of the box about the endpoint and moment of inertia of the circle about the same endpoint. So the distance is going to be higher. How do you do that? Well, in general, complicated, but in practice, not as much. You can do that using something called parallel axis theorem. Parallel axis theorem. You have seen the same theorem, but in a slightly different context, maybe in mechanics of materials. Was it in static? No, in mechanics of materials. I don't know if you have had that already or not. Yeah, actually, never mind. Pretend it's new to you. If you have seen it, it is the same thing. If you haven't, don't worry about it. So it's this parallel axis theorem says if you have any randomly shaped body and you know the moment of inertia about an axis that passes through the center of mass, and if you want to calculate moment of inertia about another point, let's call it point A, an arbitrary point, you can calculate that. I about A is going to be I about G plus total mass of the object multiply the distance squared. Distance is always from the center of mass. Well, the proof is relatively easy. I'm not going to go into it. But this is how you can calculate moment of inertia about an axis that is parallel to the one passing through the center of mass, but the distance d away from it. And this m is total mass of your body, rigid body. Or not total, let's call it mass. So going back to this example, usually I know moment of inertia about the centers of mass, and I can IG1, IG2, I can calculate moment of inertias about these additional, well, not additional, this distant force. This is some distance d1, this is some distance d2, and I can calculate moment of inertia of each of these two shapes about this distant point and then add them together. That is how we do things, usually. Oh, one other thing. Sometimes to simplify calculations, imagine this hammer has a circular hole. If you want, you can actually do the more or less the same thing, but subtract the moment of inertia of a smaller, well, circle, the hole, from the rest, and in that case you have to actually calculate the moment of inertia of that hole relative to your new reference point and subtract that. So you can have add some negative moment of inertia to create Hall effects. What else? Oh, one other thing, a couple of things. Well, you can mathematically see it in the parallel axis theorem, but also intuitively. Note that moment of inertia, it depends on the squared of distance. So as the distance of a particle to that axis doubles, its rotational effect quadruple. So this extra effect of distance from the center is very important. And first of all, that is one thing, that you have these flywheels, these big wheels that kind of smooth out rotational motion, like in car engines or in old locomotive, steam-powered locomotive cars. You had these big wheels far from the center of rotation. That is because of essentially distributing the same mass at larger distances that creates higher moment of inertia, and that resists changes in angular accelerations more, and it smooths out the motion. So distance matters. The more distance, the squaredishly the effect in rotational domain. So that's one thing. Another thing, note that the point where all particles have the smallest distance is the center of mass. Essentially, center of mass is where you have the lowest amount of moment of inertia. You can see it in the equation of parallel axis theorem. As you move away from center of mass, your moment of inertia increases. But you can also intuitively think about it, that center of mass being the most central point has the smallest kind of effective distance to all other particles. That's that. The last thing, the last concept I want to mention is radius of gyration. In many situations, like if you have different parts, you're looking at data sheets, or you want to transfer some information to another person, and you want to maintain some level of generalizability. So someone seeing a part with the same shape but different dimensions, maybe they can calculate the moment of inertia. Often you don't report the moment of inertia itself, rather a metric that is related to that, and it is called radius of gyration. So if you have a body, some point, doesn't matter if it's center of gravity or not, you calculate moment of inertia, let's call it IA, whatever, with the integral, you have some amount. You can write it as mass times some distance k squared. This k is what we call radius of gyration, and that is a value you can report and communicate to somebody else. Alongside with the mass of the particle, they can calculate the moment of inertia. Effectively, this radius of gyration means if you have the same body, but it is essentially distribute all the mass along a thin ring that has the radius k, these two systems will have the same moment of inertia. So that's a good way you can communicate moment of inertia with some level of generalizability to somebody else. thinking, is there anything else I need to say? No. Okay, so that is all about moment of inertia. Lots of information, but as you can imagine, it is a central concept in rotational kinetics of rigid bodies. That's why we spend so much time on it. And the equations, we'll get to them in the next video. Well, let me get to the next video. So I'll see you in that video when we discuss equations of rotational motion. So see you then.